First of all, I'd like to thank you for your invitation. It's a pleasure for me to be here for the first time. It's the last contribution before another coffee break, and I will try to make a brief presentation of this problem, this work, which it's still in progress. And the main reason for this evaluation, for this approach, is that the current agricultural practice, the current agricultural works, consist in uniform irrigation, fertilization, and application of special treatment, without taking in consideration of the heterogeneity of the area, lithological, pedological, or morphological aspects. And we have some instruments to improve that situation. And that instruments are remote sensing data, especially satellite image, and GIS application. Why? Because we're using these instruments, we can have an efficient land cover at medium and large scale. We have low cost per surface unit. One image providing by Formosat, for example, Formosat 2 satellite, have a price of €3,000, but the surface covered, it's 650 kilometers. That means somewhere between €4.50 per square kilometers. And we have an unified approach of data, common solutions, and easy to use this evaluation, this technique after the first fundamentation. A few words about location. We have a case study, and the location, it's agricultural area Ștefan-cel Mare in Călăraș County. It's a typical area, agricultural area for our country. Situated in the southeast of Romania, something in this position. The area is a tabular plain made of loessite deposits, different loessite deposits. You have on the slide the lithology of this area. Between Ialomița River and Borcea Brent. Shallow aquifer with a water table at 10 meters deep, and resource and methodology. I use the remote sensing data, the satellite image, as I say, the high resolution image provided by Formosat 2 satellite. The spatial resolution for this image is 2 meters for a panchromatic, black and white image, and multispectral 8 meters for multispectral image. The image, it's the same image, but it's taken with two sensors, two different sensors. One sensor, it's panchromatic, and one sensor, it's color, it's multispectral. And it's taken the same time on the same surface. Other characteristic of this satellite, it's sensor footprint, 24 per 24 kilometers, revisit interval daily, and panchromatic and multispectral image can be acquired in the same time, as I say. Image size, file size, it's 137 megabytes for panchromatic image and 35 megabytes for multispectral image. Data delivering format, the file it's in GeoTIFF format, and delivering time for online command, it's 24 hours, basically. Software resources that utilized is MVX for image processing and analysis, ArcMap 10 for as GIS platform, and Ansat Suite Plus for unsaturated media modeling, and Visual Mode Flow for aquifers modeling. All this work with remote sensing data, it's correlated with fieldworks, because the key problem, the key aspects of this approach is to correlate these two types of interpretation in order to obtain a understanding of spectral response on the satellite image. The satellite image consists of a number of pixels, many pixels, which the different color or different value, and each pixel have a signification in correlation with the real situation. Okay. Sampling and analytical work, it's all field campaign. It's consists in a preliminary stage of data collection. As I say, the work is still in progress. And we take 5 groundwater samples and 9 soil samples. We have the coordination, geographic coordination for each sample. And we have the result of this analysis for nutrients, because all this work is related to agricultural works, agricultural practice, and we are interesting to evidence this content of nutrients. For nitrate, the groundwater samples are the value from groundwater for nitrates. It's exceed the threshold value for one sample except one, for all samples except one. And this concentration shown in this table, it's more significant because the unsaturated zone is thickness with 10 meters, and that offer a good protection to the aquifer. In this table, you see the results of analysis for soil samples, and data correlation or interpretation, a logical scheme, logical chart. We have satellite image, raw satellite image. Using this satellite image, we have for the first defined some region of interest, ROI, region of interest, which consists in a working area, effective working area. On this new results, working area, ROI of region of interest, we are doing a vegetation delineation in order to obtain a highlighted vegetation of this area. In correlated with all these results obtained for the field work, we have a classification. We have a classification, and the new result of it's a new image with classes of information. All these data are integrated in a GIS application as spatial databases and attribute databases. On this slide, you have the image of all these steps. In the first 2 images are the satellite image, raw satellite image, panchromatic and multispectral, the same surface, the same zone, the same moment, at different resolution, 2 meters and 8 meters. After this segmentation, this region of interest are obtained for working area. It's a small area. Okay. As I say, we have here a vegetation delineation based on the multispectral image using near-infrared and red bands. And on this new image, we have 3 types of area with no vegetation, brown, and 2 areas with different level of vegetation, taking in consideration only the spectral response of this vegetation on the satellite image. After this step, the next step is classification, unsupervised classification. And this image have 3 different classes, and this classification is made using multispectral image. In the same time, I do pan-sharpening. This is an operation which that result a multispectral image at high resolution based on the image, panchromatic image. On this new image, multispectral image, at 2 meters in this time, we have a more refined, a more accurate classification of for a small area for best results. All this data, all these classes are export. In this step, the classes here are in raster form. It's export as vectors, and this shapefile, these vectors, are taken in a GIS application. You have here this shapefile with vectors. Is the same image but in other format, and the attribute table of these vectors. Okay, the results. The results is the variability map, and on this variability map, each classes, each characteristics on the map have corresponding in the field with a stage of tissue, of vegetal tissue, with stage of agricultural, of crops, or a stage of water content from the soil, and so on. Conclusion. Based on this correlation, the interpretation of remote sensing data will become an important instrument for evaluation and taking the right decision for improvement of the agricultural work and reduce the negative impact of soil and groundwater. Due to the specific and strong spectral response of the soil water content variation, the proposed methodology is very efficient for evaluation the soil water demand. The irrigation improvement will maintain a proper soil water content and will provide a reduction of water used for groundwater pollution. Further steps, correlation with GPS capability for agricultural campaigns, and why not integration of additional data comes from geological environment modeling. Thank you very much.